The title of this notes is Parametric Equations, and the outcome is that you're going to be able to write a conic as a set of parametric equations. So I want to start with explaining what parametric equations are. So I have an ellipse here, and when we're talking about things orbiting, you're going to imagine that the path of the orbit is an ellipse. So here's an object, and the object is moving over time. And depending on the time, the object is in a different location. And so what a parametric equation does is it tells you the location of an object at any certain time. So time is always an independent variable. And our equations right now for an ellipse, they don't have time in them. So what we're going to do, I'm just going to make up an equation of ellipse. What we're going to do is we're going to bring time into the equation. Where's time? It's going to be a lowercase t. And so we're going to use that, use a parametric equation in order to do that. So what I want you to think about is, think about this object as if it's rotating around the ellipse, and think about just where it is on the x-axis. So as this object moves around, where is it on the x-axis? And what I hope you see is that it's bouncing back and forth. Likewise, let's think about where that object is on the y-axis. Again, I'm going to take this object, and it's going to rotate around and around and around the ellipse over and over and over again. If I'm looking just at its y motion, that object is bouncing up and down and up and down and up and down over and over and over again. Do we know any functions that bounce up and down over and over and over again? We do. We have our sine and our cosine functions. They bounce up and down over and over again. So I want you to take a look at this equation. It happens to be of an ellipse. And I'm just going to tweak the equation a little bit. We know that the denominator of the x term is 7 squared and the y terms is 12 squared. So what I want to do, because both the because both the numerator and the denominator are squared, I want to write the fraction like that. I actually don't need those parentheses in the numerator. And I can put the square outside the fraction. I can do the same thing for the second fraction. So that's another way of expressing that same conic equation. And what I want you to hopefully see is that really what this equation is we have something squared plus something squared equals 1. Do you know any equations where something squared equals 1? In fact, you know your Pythagorean identity. Sine squared x plus cosine squared x equals 1. And we're going to be using that identity to make our parametric equations. So writing parametric equations, this means I give you a conic like you just saw on the last slide, and you're going to turn it into a set of parametric equations. The set means you need two equations. You need one to describe the x motion and one to describe the y motion. So the first thing you're going to do is you're going to rewrite the equations as two squared terms. Then you are going to set the x term equal to cosine squared t and solve for x. We have to use cosine because if you think of your unit circle, cosine is always in the x position. You're going to do the same thing for y squared, but you're going to set it to sine squared t and then solve for y. So I'm going to pick up that same problem you saw me starting on the last slide. So step one is what we did on the last slide. Rewrite this as one big squared term equals 1. That's step one. And our Pythagorean theorem says sine squared plus cosine squared equals 1. We're going to align the cosine squared to the x squared term. So x plus 2 over 7 squared will equal cosine squared t. And we want to solve this equation for x. So what we're going to do is we're going to take the square root on both sides. That's just going to cancel out the squares. So that gives us x plus 2 over 7 equals cosine t. And where you want to get rid of this fraction, multiply both sides by 7. X plus 2 equals 7 cosine t. And then we're going to subtract 2 from both sides. We like to write the minus 2 in front of the cosine. Typically, you never want to write anything after trig. the trig stuff should always go last in an expression. It doesn't have to, but it's a good practice to keep it there. So that's the equation for x. Now we're going to repeat this process for y. So I'm going to go back up here and I'm going to find that y minus 1 over 12 squared. I'm going to set that equal to sine because sine is always going to represent the y term. So setting that equal to sine squared t. Go ahead and take the square root of both sides to cancel out the squares. And then we're just doing algebra to get y by itself. So we're going to multiply both sides by 12. And then we're going to add 1 to both sides. And again, we're going to put it in front because we don't like to write stuff after a trig. So we have two equations, one to describe the x motion over time and one to describe the y motion over time. And typically what we do is we write the x equation over top of the y equation. And you would want to see both of those equations right on top of each other as your answer. Now we're going to go the other way. We're going to talk about what happens if you start with parametric equations and then you want to flip it into standard form. So standard form are called implicit equations. That's because they don't have y equals. Y equals is an explicit equation. You explicitly know what y is. We are implying a graph. So they're called implicit equations. So you're just going to work it backwards. You're going to first isolate cosine t and sine t. You're going to square both terms. And then you're going to use that Pythagorean identity again. Cosine squared plus sine squared equals 1 to make your equation. So let's look at a quick example. So step 1, I want to isolate cosine and sine. So in the x equation, what I'm going to do is I'm going to add 6 to both sides. So x plus 6 now equals 1/2 cosine t. And I want to get cosine by itself, so I'm going to multiply both sides by 2. So 2 times x plus 6 equals cosine t. And then I'm going to do the same thing for the y equations. Get sine by itself. Oh, that one was easy. It already is by itself. Okay. So this in green is equivalent to cosine, and the blue is equivalent to sine. Now what I'm going to do is I'm going to think about my Pythagorean identity, which says sine squared plus cosine squared equals 1. Order of addition doesn't matter. So I'm going to write the cosine first. So I'm replacing cosine in this identity with this stuff. And I'm going to replace sine with this stuff. And now I just want to make it look like the equation of ellipse that I'm used to. The y is good. There's no denominator there. This is kind of funky. I purposely did not distribute this. I have two terms being multiplied, so I can apply the square to both of them. So that's 2 squared and x plus 6 squared. And that 2 squared is 4. And there's the equation of your ellipse. So you might notice that all that we've seen so far are ellipses. So what about hyperbolas? So hyperbolas still use a trig identity, except we need something squared minus something squared to equal 1 to make a hyperbola. So if you think of your trig identities, remember I don't have these memorized. I only have this one memorized. What I'm going to do is I'm going to divide everything through by cosine squared. This will give me another identity. It's on your goldenrod sheet back from second marking period, but you don't need it because you can just memorize it. Memorize the first one and derive it, I mean. 1 over cosine is secant squared. Okay. And I want this to equal 1. Okay, so right here, this is 1 plus. Sorry about that. That's a plus, so that's a plus. Okay, so I want this to equal 1, so what I need to do is I need to subtract tangent squared from both sides. So 1 equals secant squared minus tangent squared. And then that's what you would use to relate it to the equation of a hyperbola. So we're going to stop there, go ahead and draw your line, and we're going to do a lot of practice of this in class.